Myself, Dr. Charmila, working as an associate professor, Department of ECE, Rajkumar Goyal, Institute of Technology. So, in this lecture, you are going to learn about the one of the hardware description language which is used in the semiconductor industry, that is Verilog. So these are the topics I am going to cover in this section. We are going to see about what is Verilog, why it is developed, and what are the different applications of Verilog. And we will see the some of the important concept of VLSI design, such as digital design flow and design abstraction level. At last, we will see about the some of the software tools required for the hardware description language. So these are the learning outcome of this lecture. After completing this module, you can able to understand the basics of Verilog HDL and you can explain what are the different applications of Verilog and you can define the basic difference between FPGA and ASIC concept. Then you can describe the digital design flow and you can identify the different level of the abstractions in your chip design. Then you comes to know the basic simulation tools available. So first, why you have to study the Verilog? So in order to understand this, let us compare the traditional circuit designs with modern chip design. So if you are taking the traditional chip circuit design, in the early days of the electronics, the circuits are very small and simple. So these circuits are just made up of a logic gates such as AND or NOT, XOR, multiplexer and decoder. So these circuits contain the few components. So it can be designed manually with your hand and it can be the implemented. But in case of modern chip designs, so digital circuits are very complex and large. So example, you can take any of the modern electronic device such as mobile phones, computer, desktop or AI accelerator. So these devices contains the processor. Here I have given some of the examples of a processor: Intel, AMD, NVIDIA, GPU, Qualcomm, Snapdragon processors. So these processors contain the millions and billions of your transistors. So designing the millions and billions of transistors by hand manually, it is impossible. So that's why we are going for the hardware description language. So the hardware description language is mainly used to design a complex digital circuits. So in the hardware description language, we are not going to draw the uh, digital circuits manually. Instead, we are going to write the code. With the help of the code, we are going to describe the functions and behavior of your circuits. So the hardware description language allow the engineers to design, simulate, test as well as verify the digital circuits. So the main advantage of the hardware description language is with the help of this one, we can improve the speed of the design and reduce the error, increase the accuracy and efficiency before a chip manufacturing. So next we will see what is Verilog. So generally the Verilog is a pro language. With the help of this language, we are going to write the code which will describe the digital circuits. So the Verilog is a hardware description language which is used to describe the structure and behavior of your digital circuits with the help of writing a code instead of drawing the diagram manually. So once the code is written, we are going to use a simulation tool to verify the function of your code, right? So once it passes all the simulation tests, next we are going to use the synthesis tool. The synthesis tools convert the Verilog code into the gate level netlist. So with the help of the Verilog, we are going to design the complex digital systems quickly, accurately, as well as efficiently. So the main advantage of Verilog is we are going to write the programming code. This code can be simulated before the implementation. The simulation helps to verify the functionality and detects the error at the early stage. If there is any error, again we are going to modify the code and we are going to perform the simulation. Once the design passes all the simulation text, next we are going to use the synthesis tool, which converts the Verilog code into the hardware implementation, that is in the form of your logic gates and circuits. So because of these advantages, the Verilog is widely used in the semiconductor industry for designing a digital integrated circuit. So next we will see what are the advantages of Verilog. So if you know any of the programming language like C, C++, Python, then Verilog is easy to learn because the keywords, operators, as well as syntax are more or less same as the C programming language. But the Verilog is not a programming language. It is a hardware description language. So another advantage of Verilog is it supports the simulations. Once the code is written, the code is verified with the help of using a simulation tool. Next, it also supports a synthesis. Once the code passes all the simulation tests, next we are going to use the synthesis tool to convert the code into the gate level netlist. Then last advantages, here I have mentioned this, the Verilog is compatible with FPGA as well as the ASIC technology. So where the Verilog is used means the Verilog is widely used in the semiconductor companies such as Intel, AMD, NVIDIA, Qualcomm, Broadcom, Texas Instruments, and Samsung. So before manufacturing the any chip, the designers implemented with the help of using a Verilog. They are going to use the code to design a digital circuits. So generally they use a Verilog and system Verilog for the chip development. So next we are going to see about the two important terms you frequently hear in a digital circuit, that is FPGA and ASIC. So why we have to learn about the FPGA and ASIC means once a circuit is designed with the help of using a Verilog code, once the code has been written, so next we are going to next step is we are going to implement it. So it is implemented either in a FPGA or in a ASIC. So after the in order to perform the implementation, two options are there. One is FPGA, another one is ASIC. FPGA stands for the Field Programmable Gate Array. So what does FPGA means? It is generally a hardware chip. So this chip can be the reusable and reprogrammable. So once a code is written using a Verilog, we are going to convert that Verilog code into the bit stream, and then these bit streams are downloaded and uploaded into the FPGA board. So the main advantage here is if you find out any error in the code or if you want to update the features means, so we are going to modify the Verilog code again and then download again in the form of a bitstream, upload the bitstream into the FPGA board. So the main advantage is you can program the FPGA board multiple times. You can erase and reprogrammable it multiple times. Okay, so the another advantage is it is a lower development cost. It is mainly used in a design and prototyping stage. So this FPGA board is best for learning, research, testing, and prototyping. So some of the popular FPGA vendors are Xilinx and Intel. So next we will see the second option for the implementation, that is a ASIC, that is application specific integrated circuit. So from the name itself, you can define that it is mainly designed for the one specific application. So once the programming code is once it is designed, it cannot be modified after manufacturing. So the main advantage of ASIC is it provides a high speed, it consumes a less power, and it provides a better performance. As compared to the FPGA board, it is a smaller in size. So the ASIC is mainly suitable for the large scale productions. So next we will see the difference between the FPGA and ASICs. So here the FPGA is a reprogrammable. Already I told you FPGA is a hardware chip. It can be the modified and reprogrammable one. But in case of ASIC, it is a fixed one. Once it is manufactured, it cannot be changed. So the advantage of the FPGA is the low initial cost, but in case of ASIC, it requires a high initial cost. As compared to the ASCII, FPGA is a slower one. So the FPGA is mainly used for the design and prototyping. The ASIC is mainly for the mass productions of any of the chips. So why you have to learn FPGA and ASIC with Verilog means already you know that Verilog is mainly used to design a digital hardware. So once the Verilog programming code is written, you can download that programming code and upload it on the FPGA for the design, testing and prototyping. After it pass all the verification, the same design can be manufactured as a ASIC for the commercial product. So mainly the ASIC is for the mass productions. So in understanding this FPGA and ASIC helps you to explain the complete hardware design flow. So next we are going to see about one of the important topic of VLSI design, that is a digital design flow. So generally the digital design flow explains the complete procedure of designing a chip starting from the idea into the final manufacturing product. So here we are going to see the step-by-step process of developing a digital chip. So first stage is nothing but a specification. So generally the specifications describes what the chip should do. Here we are going to define the functionality and the requirement of the complete system. So for example, the company wants to manufacture a smartwatch processor means here they are going to specify the specification at the initial stage. They will specify that low power requirement and Bluetooth interface, Bluetooth support, sensor interface and all. So after the specification stage, next stage is nothing but a architecture design. In the architecture design, we are going to divide the complete system into a smaller block. Then we are going to define how these blocks will communicate with each other. So after the architecture design, next important stage is the RTL design. The RTL stands for Register Transfer Level. Here we are going to define how the data transfer between the registers, how the ALU perform the arithmetic operations, how the control logic behaves. So these are the things explained in the RTL design. These are the main function of the RTL design. Here we are going to use the Verilog code to describe the function of a digital circuits, right? So once you have programming, once the Verilog code is written, the next step is nothing but a simulation and verification. In this simulation stage, we are going to verify the design, whether the design is working as expected or not. Okay, so in this stage, we will provide a different set of input value and observe the output. So if the output is correct, then we will go for the next stage, that is nothing but a fifth stage, that is a synthesis. Here we are going to use a synthesis tool to convert the RTL code into the gate level netlist. Okay, so after the synthesis, the next stage is nothing but a physical design. In the physical design, we are going to define where we are going to place the components in a chip. Exactly where we are going to place the transistors in a silicon layout. That is defined in the physical design. Apart from that, where to place the component, we are going to define how the components are connected with the help of using a metal wire. Okay, so the physical design mainly defines the where to place the component, how the connections are given between the components. Okay, so after the physical design, the complete design is given to the fabrication. Okay, so that means the complete design is sent to the manufacturing plant. So in this manufacturing plant, we are going to send the layout in the form of GDSII file to the fabrication. Here they are going to use semiconductor, they are going to use the fabrication technology to design the final chip. After the fabrication, next they are going to perform the testing and validation to perform the reliability of the test. So these are the complete steps from starting from the specification to the fabrication. It will explain the complete digital design flow. So next we are going to see about a design abstraction level. So in this design abstraction level, we are going to see about in this digital abstraction level, we are going to divide the complex digital circuits into the different level of the abstractions, right? So the abstraction means how we are going to manage the complexity by dividing a design into the different level. So each level provide a different level of details. So the abstraction level generally specifies the design by hiding the unnecessary details. So here we are having a 5 different levels starting from the architecture, RTL, gate level, transistor level, and physical level. So the architecture level has the high level of abstraction, means which provides the what system should do. Okay, so here we are just going to see about here what are the main components are there in the system. We never discuss about the internal implementation details. The physical level provides here more detailed informations about your chip design. So let's see one by one. First one is the architecture level. It is the highest level of a digital system design. Here mainly we are going to focus on the overall system architecture. So which means what are the blocks are required, how the blocks are communicate with each other. Here we never discuss about internal implementation like how very not about logic gates and Verilog coding at this stage. Here just we are going to identify what are the major functional blocks are there in your system and how these function blocks are going to communicate with each other. So the main key design decisions is just we are going to discuss about number of processor core processor required, how the memory, what memory size is supported by the processor, and the graphical GPU supports a oscillator requirement, and how the blocks are going to communicate with each other. So the example for this architecture level is if you want to build a home, the architect will provide only the house blueprint. Here they will provide number of rooms, living rooms, kitchens and all. They never discuss anything about the internal implementation details such as the size of bricks, what type of cement they are using it. So like an architecture level, it will just provide a overall system structures only. So after the architecture level, the next level is nothing but the RTL level. RTL stands for register transfer level. So this is the second level of abstractions in your digital design. So here only we are going to use a Verilog HDL. Generally, this Verilog HDL describes how the data communicate between the registers and how the arithmetic operations will perform and how the control logics will behave. Okay, so the RTL main important RTL components are registered, data path, arithmetic logic unit, and control logic. So the example in case of architecture level, if you want to perform addition of two number in the architecture level, we just decide in order to perform the arithmetic operation, we need a adder. But in case of RTL level, in the next stage, we are going to use a Verilog code. Here we will describe how to perform addition of two inputs. Okay, so for that we will describe how the data transferred from the registers and how arithmetic logic unit will perform the operation, how this operation is controlled with the help of using a control logic and all. So the main important thing here, we are going to use a Verilog code. We are not going to draw any diagram. So it is independent of your manufacturing technology. The same RTL code is implemented using a different fabrication technology such as 180 nanometer, 90 nanometer, 45 or 5 nanometer. The RTL code will be remain same. So here the main goal is we are going to convert the system architecture into the detailed hardware description. After this RTL, we are going to synthesize it using a synthesis tool to the logic gate. So the next level of abstraction is the gate level. In the gate level, the RTL code is converted into the logic gate using a synthesis tool. Here only we are going to represent the actual digital hardware, right? With the help of a gate level list, we are going to implement the logical implementation. So what happened at this stage means, once you have written the Verilog code, we are going to convert the Verilog code into the network of a logic gate. Here we are not going to draw any diagram manually. So synthesis tool automatically generate the gate level list. In the architecture level, as I said earlier, just we are going to decide that we need a adder block. In the RTL, we are going to describe the function of the block by using a Verilog code. We are going to write sum is equal to A plus B. In the gate level, this code is converted into the actual logic gates. Okay, why is gate level is very, very important means in this level only we are going to draw the actual digital logic diagram. Then in this stage also we are going to use gate level simulation to verify the synthesized circuit behave as same as the RTL design or not. Here also we will perform the verification basically. So next one is a transistor level. So if you are taking any of the chip, we okay, the chip does not contain the physically contain the gates. Instead, this logic gates are built using a tiny device called a transistor. So generally we use the CMOS transistor. It is a combination of PMOS and NMOS. So all the complex circuits requires the millions and billions of a transistor. In this transistor level only, the engineer mainly focuses on the size of transistors and the switching speed of a transistors, that is on and off time period, then the power consumption, the propagation delay, signal integrity. So these things are mainly focuses at this transistor level only. So okay, so why it is very important means, so this level only determine the speed, power, as well as the overall performance of the circuit. So this level helps to understand the how logical gates are the physically implemented. So the next one is your physical level. It is a final stage of a digital chip design. So after the synthesis, the design is converted into the actual chip layout. Here only we are going to decide where to place the transistor on a silicon wafer. Okay, so here the major steps are placement. First, we are going to decide where to place the physical component on the silicon wafer. Next one is a routing. Routing means how these components are connected with the help of using a metal wire. Next, we are going to decide the clock tree design. Means we are going to distribute the clock signal to the all the register. After that, we are going to verify the complete layout using a DRC. So generally this layout we will call it as a we draw with the help of using a stick diagram manually. So here the design rule check verify the complete layout using a DRC. After that, we are going to perform the layout verification to ensure that the layout matches the exact circuit design. So whatever the output we are getting, that output will be in the form of GDSSII file. Okay, then this GDSSII file is sent to the semiconductor fabrication plant. In the semiconductor fabrication plant only, they will manufacture the chip on a silicon wafer. So the main important goal of this physical level is we are going to transfer the logic design into the manufacturable chip, silicon chip. So here only we are going to ensure the functionality as well as the manufacturability of the chip. So these are the different level of abstraction. We are dividing the complex circuits into a different level to make the process simplified. So next we are going to see the simulation tool. Why? First you have to know why the simulation is needed. So once you have write the Verilog code, it is very important to verify the design before manufacturing it, right? So with the help of the simulation tool, we are going to test the design with the help of giving a different input value and checks the output. If the output is correct, then we are going to proceed with the design. If there is any error, we are again going to modify the code and detect the error and fix it at the early stage. So generally the simulation helps to save the time, cost as well as the effort. So next we are going to see some of the open source simulation tools are available such as ICAS, Verilog, GTK Wave, Verilator. These are the some of the open source simulation tools are available. It is used by the students, researchers and beginners. Then some of the commercial simulation tools are also available. Model Sim, Quester Sim, CAD and Zillium and all. These tools are mainly used in the semiconductor industry for advanced verification and debugging. Okay, so what is the main advantage of this simulation tool is with the help of the simulation tool, we can verify the functionality of the circuit. If there is any error, you can find out at the early stage before fabrication. So it will reduces the development cost as well as it will improve the design readability. So these are the advantages of using a simulation tool. So we are at the end of the lecture. So here we will see the summary. So in this lecture, I have discussed about the basics of Verilog. As I said earlier, the Verilog is a hardware description language. Here we are going to write the code instead of drawing the digital circuits manually. So as I said earlier, once the code is written for the implementation, we will go for FPGA and ASIC design. You know, the FPGA is a reprogrammable one. The ASIC is a fixed. Once you have manufactured chip, it is not able to modify it. Okay. So already I discussed about RTL. In the Verilog is mainly used in the RTL stage. It is one of the important stage in the abstraction level. So then I discussed about the simulation. The simulation is very important to verify the functionality of your design. Okay. So in the modern chip designs, the Verilogs are used. So thank you for listening.